Jingji Zhu is going to present exploiting just noticeable differences of delay for improving quality of experience in video conferencing. And as soon as we have a picture.
No, later. You can sing away and I will do it. Okay, thanks. Hello.
Okay, great. Let's go.
Okay. Good afternoon, everyone. My name is Jinxi Xu. I'm from the Department of Computer Science and Engineering of the Chinese University of Hong Kong. Today, I will present a method for improving the quality of experience in video conferencing systems. This is a joint work with Professor Benjamin Wang. So in this research, we care about the static quality of experience in video conferencing systems. Previous works have shown that it consists of two aspects. Firstly, the signal quality, that is the quality of video and audio. They represent how good the content can be shown to users and may be affected by the data compression and transmission error. Secondly, the interactivity or the ease in communication. Because a video conferencing system is not only a streaming system, but also an interactive one, the smoothness of the conversation should be also taken into consideration. A good quality is always desired in a video conferencing system. However, it cannot be assured in a best effort level. Here, there are two level impairments which may degrade the quality of experience of a video conferencing system, and we have videos for demonstrating the effects of these impairments. First, delay jitter is a large fluctuation of delay in the transmission. The delay may suddenly increase to several hundreds of milliseconds and return to the normal state soon. This may cause late arrival of many packets and may fix the transmission of the video. And losses are drops of packets in the transmission. If the lost packets are not recovered correctly, then it may lead to misplacement of many video blocks. Either of these impairment will reduce signal quality and thus the QoE. So to avoid it, channel level methods are generally used in video conferencing to fix the impairments. So to deal with delay jitter, we can increase the time waiting for the late packets to smooth the playout of the video. And to recover the lost packets, we can add redundant packets into the packet flow so that when a packet is lost, we can recover it with a duplicated one if it is correctly received. But both of these methods need extra time for producing and for the receiving these extra packets. Unfortunately, in real-time video conferencing, the delay cannot be too much long because it directly relates to the interactivity. So we will show the effects of delay in details. We consider a two-way conversation. For example, in a face-to-face conversation, when A speaks something, B can hear it immediately. However, in a transmission channel with delay, after A speaks something, B should wait for some time to hear for that. We cause the delay of a speech from being spoken to being listened as the mouth-to-ear delay. If this delay is too long, for one hand, both A and B will find the conversation inefficient. For the other hand, A and B will find the conversation asymmetric or unbalanced. To measure the efficiency of a conversation, we can simply compare compute the fraction of time for speaking and hearing in the whole conversation. If this can refer how long the silence is in the conversation. To measure the imbalance, we can simply compare the shortest silence and the longest silence in a conversation. If there is a long delay, then someone may find that he needs to wait for a longer time for the response than the others. So because both good signal quality and interactivity are desired, there are trade-offs when optimizing the QoE in video conferencing system. A best trade-off is not easy to achieve because in different level conditions and conversational conditions, there are different priorities of these requirements. However, we find that finding a better trade-off is much easier. For example, if we find that the interactivity is already very good and the signal quality can be significantly improved with just a little increase of MED, then we may find that increasing MED is a wise choice. Unfortunately, existing video conferencing systems do not always make wise choice. This figure shows the QoE of Skype in a level with delay jitter. In the first figure, the z-axis shows the video quality, and the x and y-axis show the efficiency and the imbalance of our conversation. We find that by a little increase of the MED, the signal quality can be greatly increased. But the efficiency and the imbalance of the conversation is slightly increased, and we also find this in the audio quality. And we also measure another system, Windows Line Messenger, and also find that it operates as optimally in a loss level. This inspires us to study a method for improving the overall QoE of a video conferencing system by choosing the operating point right. We propose to increase the buffering time for packets or the overall MED because we have found that this can always help improve the signal quality in a variety of level conditions. We want the increase of MED to be done without degrading the interactivity. Otherwise, the QoE may not benefit from this adjustment. So now the key problem of this study is how to do the increase of the delay insignificantly. That's the key problem of our research. We thus propose to use a concept from psychophysics called just noticeable differences, which utilize the limitation of a human's perception to increase the buffering time. For example, if the original delay is 200 milliseconds and the new one is 300 milliseconds, then many people can figure out the longer delay. On the other hand, if we increase the delay by just 20 milliseconds, then much fewer people can figure out the differences. However, it's worth mentioning that 20 milliseconds can significantly benefit the video conferencing system because it can smooth the late arrival of many late packets and also can recover several lost packets. We have performed a detailed study on the current internet to see the benefit of increasing the buffering time. A worldwide overlay network PandyLab was used to collect the data. The traces was collected and selected with randomly select and paired loads, and totally more than 10,000 traces were collected. We then classify these traces into 10 classes according to the loss rate, the delay, and the jitter. And we find that there are 24% of the traces have captured level impairments showing different levels of loss or jitter. Traditional methods use rate control to eliminate the loss and delay jitters. Although they are useful in many links, there are still a few links that do not react to the rate control. That is, loss and delay jitter still exist even though the bill rate has been reduced. However, we find that a longer MED can always help buffering more late packets and recovering more lost packets, thus reduce the ratio of unavailable packet rate, or UPR for short, within the MED. UPR can represent how good the content is shown to users because it shows the complete list of the video content in the transmission. So this figure displays the UPR in a level connection from Ohio to North Carolina. Blue box here represent a low UPR, and the red box here represent a high UPR. And we can find that the UPR can always be reduced when the MED is increased, no matter what the sending rate is. We also measure the UPR in different kinds of level connections throughout a day. And the figures here shows that in different level connections with delay and jitter, increasing MED can always help reducing the UPR. This supports the generality of the proposed method in current internet. So we define the GND of delay in a statistical way. Here we let pixel to be the fraction of subjects who correctly find the differences of the two given sessions. And we say that 75% GND of a given delay is the maximal distance from a given delay MEDA that let pixel no larger than 75%. Although both 50% GND and 70% GND are often used in psychophysics, here we only use 75% GND because 50% GND can be attained by the user random guess, but 75% GND should be attained when the user actually perceives the difference. So according to the definition of GND, we have conducted comparative study tests to measure it in different conditions. A test is performed in a way that two video conference recordings, just like this, are presented to subjects in random order. This video have the same content, except that they have different structure because they have different delay. We then let subjects determine which one has the longer delay. We show one set of the test, for example. Excuse me, the audio, thanks. Thank you. Good. This is a video with 50 milliseconds delay. And in the second video, the MED is set to 1000 milliseconds.
Hi.
How are you?
I'm fine.
Okay, then users are asked which video has longer delay. And finally, we will record the fraction of subjects who can correctly answer these problems. This is one set. We can fix the starting point MEDA and extend the delay to different values to measure the correct list of the answers at different points. Finally, interpolation was used to find the 75% GND. And this is the method we get the study test results. With this method, we can measure the GND in three level conditions and with a fast and a slow conversation. Several results are attained. Firstly, GND becomes larger when MED becomes larger. That means that if the base MED is large, then user can tolerate a longer extension of the delay. Secondly, when the video conferencing is streamed in a lossy connection, then the relation between JND and MED is similar to that in the lossless condition. But when we stream the video conferencing data in a jittery connection, then we find that JND is larger when the MED is small and is stable when MED becomes larger. It may be caused by that the lay arrival of packets will freeze the video and confuse the way humans can perceive the delay. Furtherly, GND is larger in a slower conversation. This indicates that the conversation time frequency may change the sensitivity on delay, and that a slower conversation can tolerate a longer delay. Finally, GND increase linearly with MED. This helps us to estimate the GND at the MED points that we have not measured. We also observed that the GND is reasonably large in different conditions. With this measure, we can improve the delay by GND so that the user cannot perceive the differences in delay. And this extension of the delay can be used to do more buffering and do more recurring of the data packets. To validate the availability of the proposed measure, we have deployed an interceptor in Windows to make the delay buffer. This interceptor is delivered with Windows filtering platform and is running in the kernel mode of Windows. With this interceptor, we can add sequence number and timestamps to the packets sending out from a video conferencing software. And before this packet was received by another side of the video conferencing, they are buffered in the driver. And here, early packets are delayed so that they can wait for the late packets. And lost packets can be recovered if the redundant packets are received during this period. It's worth mentioning that this interceptor is deployed at the level layer and is transparent to the video conferencing system. Thus can be reused by any other level applications. We also developed real-thought testbed that can perform repeatable measurement for signal quality and interactivity. This testbed contains a human response which can speak and reply automatically based on a pre-recorded video. Here we insert the markers to the video, the audio, and packet streams by a virtual video, virtual camera, a virtual microphone, and by some methods in internet. And these markers are used to measure the delay to synchronize the videos when we measure the signal quality. And a level emulator is placed between the two times to emulate the level conditions in different scenarios. And these traits are collected from PennyLab and can replace the condition in real internet. With this testbed, we can measure the QoE of any video conferencing systems under a variety of level conditions. So if you are interested in measuring the QoE with this system, you can contact me. So we saw the experimental results with Skype and Windows Live Messenger. Skype originally performs poorly in a level with delay jitter. However, with our interceptor, the video quality and the audio quality can be greatly improved, while the interactivity is not significantly degraded. We can see that through the suggested test, 100 subjects choose our system as the which has the better quality. And we have done this without increasing the packet sending rate. Because we only change the delay of the packets, we can find that with the increasement of the MED, the UPR is greatly reduced. So that's the main reason we can have a better quality. And instead of only testing the proposed method with a fixed trace, we further perform more informal similarity tests with random generated traces. And the results also support that our video conferencing system has better quality. So this is the video record of one kind in the conversation. And this is the original performance of Skype. You can also see the marker in the video. And this is the performance with our interceptor. You may find that this is done without much increase in delay because we only increase the MED with GND. However, the quality is much better. And we also perform a similarly test with Windows Live Messenger. And we found that with our interceptor, the signal quality can be greatly improved, but the MED is not greatly increased. And we can see the results here. This is the original quality. You can find that many frames are lost. And this is our proposed method. These results can prove that the proposed method can improve the overall QoE in a video conferencing system. So at the end of the talk, I conclude our approach in the study. We have figured out the suboptimal operation of existing system in QoE. And after a detailed study of the internet trace, we found that increasing MED can always reduce the ratio of unavailable packets and improve the signal quality. By using the concept of JND, we can increase the MED in an unperceivable way to avoid affecting the interactivity. However, we can greatly improve the signal quality. So we validate the proposed method by deploying an interceptor in Windows to change the traffic behavior of existing systems. Finally, we use our real-time testbed to measure the QoE of our system and prove the advantage of our proposed method. So we are working on modeling the multi-dimensional GND with many quality metrics, and this will help develop a method for efficient similarity tests and can be used in future systems. And finally, we want to acknowledge Vihon Yu for providing us the raw video for similarity tests and the staff in Microsoft for advising us the usage of Windows filtering platform. Thank you very much.
Thank you.
Any questions?
Okay. Do we have? Yeah, there's a question back here.
Thank you. I'm not sure I fully understand how you did the subjective tests
Yes.
with the using the test bed.
Ah,
Could you, because I don't see how you could do a quality of experience measurements, which I assume involves humans, using the test bed.
yes, actually the test bed is used to measure the objective metrics. That is the delay and the signal quality. And our test bed can also record the video conferencing sessions and play them out to users and let them to choose which one has better quality. So this is the way we do the subjective test.
Okay, but then the scoring is done not by the users in the actual conversation themselves, but by another user who is viewing the conversation after the fact.
Yes, because we have to do repeatable measurement of the system. If we let users do some conversation with the system, then the measurement cannot be repeatable.
Okay, we should take this offline because I'm not convinced that that this does give you actually the right numbers for the quality of experience of the users who would use the system in operation. But we'll do it offline.
Okay.
That should be for an interesting coffee break, I guess. Any more questions? I actually have a quick question also following up on this. How many users do you actually had doing the assessments here?
The assessment here have about 10 users.
Okay. Okay. Also, was very nice to see actually for someone who worked at NIST with the guy who developed NISTnet that people are still using that. So that's great. Okay. With that, I would like to close this session. Thank you very much. Thank you.
Thank you very much.
Thank all the speakers again.